if you look at the universe around you, you'll probably realize, hey, I'm surrounded by stuff. And our question for right now is, what is this stuff? This stuff that makes up nebulas, that give birth to galaxies. This stuff that makes the Earth that we live on. This stuff that builds the cities that we live in. This stuff that makes us. What is this stuff? Technically, we refer to this stuff as matter. And matter is defined as anything that has a mass and occupies space. We are creatures of matter, and everything we interact with is matter. From the ocean we might swim in, to the chair that we sit on, to the air that we breathe. It's all matter. And this matter is made of distinguishable elements. That is, the air that I breathe is made of several different individual flavors or elements, like nitrogen, oxygen, hydrogen, and so on and so forth. So matter is made of individual elements, and if I look at one element, my next question is, how small does this element get? Or what's the smallest piece or grain of an element? So let's take a bar of imaginary gold, for example. If I cut this bar of gold in half, I've got 2 bars of gold. Get rid of one of them and cut that bar of gold in half again, and again, and again, and again. Do I get to a point where I can't cut it in half and still have gold? The atom is that point. When I get to a part of an element that's the size of, that is the atom, I can't cut that atom in half anymore and still have gold, still have that element. If I break that atom into smaller pieces, I'll wind up with subatomic particles. All of the atoms of all of the different elements are made of the same 3 subatomic particles: electrons, protons, and neutrons. As we start to understand how basic chemistry works for the purposes of biology, there are 2 characteristics of each of these subatomic particles you should be aware of. Its mass, often referred to as atomic mass because we're talking about the atomic level here, and its charge. If I'm an electron, I have an atomic mass of 0 and a charge of -1. If I am a proton, I have an atomic mass of 1 and a charge of +1. Proton, positive, +1. If I'm a neutron, I have an atomic mass of 1 and a charge of 0, or no charge, or you might say I'm neutral, neutron, and that's it. As far as we're concerned, there are 3 subatomic particles with these 2 characteristics, and depending on how I put them together, well, I should say the numbers that I use to put them together, I can build all of the different elements, or maybe atoms of all of the different elements. However, regardless the type of atom, I always find the protons, neutrons, and electrons in the same relative place in an atom. The protons and the neutrons are always found in the middle of the atom, in a region we term the nucleus. Outside the nucleus, in shells, or sometimes called orbitals, I'll find the electrons. So protons and neutrons are found in the nucleus, and then orbiting or zipping around outside the nucleus, I'll find electrons in their electron shells. Let's take a closer look at the atom on the left. It just happens to be carbon, and on the right we see the atomic symbol of carbon. If I look closely at the nucleus of this carbon atom, I will count 6 protons and 6 neutrons. If I look at the atomic symbol for carbon, I see the C representing carbon in the middle, and above the C I see a 6. That 6 is the atomic number for carbon, and it's specifically telling me the number of protons. The atomic number, the number of protons, determines the identity of an element. If I had 7 protons, I'm not carbon, I'm nitrogen. If I had 5 protons, I'm not carbon, I'm boron. Carbon is an atom that has 6 protons, period. Below the symbol for carbon, I have the atomic mass. Now, if we go back a couple of slides, we'll remember protons have an atomic mass of 1, neutrons have an atomic mass of 1, so if I add up the number of protons and the number of neutrons, see, electrons, their atomic mass was 0. I don't need to worry about those. But if I add protons plus neutrons, 6 plus 6, that's 12. That should give me the atomic mass. The atomic mass of carbon is 12.01. That's not 12, but it's really close. We'll talk about why we have this little discrepancy a bit later on. But before we do that, I want to take us to a periodic table where we can see all of the elements are arranged based on their atomic number, that is, their number of protons. What we're going to see in a minute is the number of protons determines the number of electrons, and later we will see it's the number and arrangement of electrons that gives an atom its particular properties, the way it reacts with other atoms. And it's because of these properties we're able to arrange the atoms in this periodic table based on their chemical properties. So let's say fluorine and chlorine are both in the same period. Because they're in the same period, they have similar properties. And we'll see why a little bit later on. The only other thing I'd like to mention before we leave the periodic table is, for biology class purposes, we're not really going to go past element 18, argon. That's as far as we're going to go. Chemistry class is where to learn about the rest of them. We're going to learn a lot of characteristics of these elements, how they interact with each other, but we do take some liberties and leave some details out because we're not concerned so much with the chemistry as what's relevant to biology. So now I'd like to jump back to that carbon that has an atomic number of 6, an atomic mass of, well, the atomic mass is 12.01. How can that be? If I look at carbon, I know it's carbon because of the number of protons. And that's it. I could put a couple more neutrons in the nucleus of this atom, and I would still have carbon. However, instead of having an atomic mass of 12, because I added 2 neutrons, each of which have an atomic mass of 1, I now have an atomic mass of 14. So if I look at this atom, which has a different number of neutrons, let's say from normal, I refer to it as an isotope. And you should look in your book at the definition of isotopes and how isotopes are used for medical technologies. But for our purposes today, we're simply concerned that isotopes are flavors of an atom that have a different number of neutrons and thus a different atomic mass. Now, when I go to figure out the atomic mass of carbon to write on the periodic table, I can't take one carbon atom and weigh it. It's just too itty-bitty, teeny-tiny small. Basically, I have to take a big box of carbon atoms, weigh them, and then calculate the average. So if I've got one isotope of carbon-14 and 100 regular carbons with a mass of 12, if I want to figure out the atomic mass, I would multiply 100 by 12 and 1 by 14 and add the two together to figure out how much all of the carbon in this box weighs. Then I would divide the total mass by the number of atoms I have, 101, giving me an atomic mass of 12.01. So the reason you see an atomic mass that's some sort of decimal, even though protons and neutrons both have an atomic mass of 1, is because of isotopes. And I can't weigh just one atom at a time. I have to weigh a bunch and calculate the average.